Okay. Particularly nice to be able to welcome Surrender Manrol from Schlumberger to join us for this. We're co-hosting this presentation to demonstrate how OpenZGY will help expedite seismic data access for machine learning using EarthNET. This will be presented by Dr. Erik Larsen from Earth Science Analytics and also Surrender Manrol from Schlumberger. So the agenda is basically just quickly go through the introductions, then Surrender will give you an overview of what OpenZGY is and obviously why this is important to the industry. Erik will then take over and give an overview of the EarthNET platform for those of you who are perhaps not familiar with our technology. Then he'll give a demonstration of how using EarthNET we've been able to leverage the OpenZGY to bring data from the Petrel project into EarthNET for machine learning processes to take place and then push it back into Petrel for conclusion, and then Q&A. Everybody's line is on mute, so please feel free at any point to put questions into the chat box. We will then have the Q&A at the end, so please collect your questions and raise them through the chat box at the end of the presentation. So with that, the introduction, I've briefly done it already. We've got Dr. Erik Larsen, who is the Customer Success Officer and a co-founder of Earth Science Analytics, and Surrender Manrol, who's Product Champion for the Geophysical Interpretation in Schlumberger. So with that, I would like to pass the presentation to Surrender.
Thank you, Sarah. Yeah, one more click, please, Erik. Thanks, yeah. So thanks, Sarah, for the introduction, and hello, everyone. A very warm welcome to all of you to this talk. And at the outset, I want to really thank Erik, Sarah, and Earth Science Analytics for inviting me for this session on openness. And as we all know, there's a huge openness momentum in our industry led by OSTU Forum, the Open Subsurface Data Universe Forum. And Schlumberger, like many others, is absolutely committed to this openness and leading this along with many other OSTU members for our industry. Now, committed to openness, you all might know Schlumberger have open sourced its data ecosystem, which is further accelerating the delivery of OSTU data platform as such. And now, continuing our commitment to openness in OSTU R3 release, which again, many of you might know, the Mercury release, Schlumberger has open sourced the ZZY format. And this is yet a phenomenal step towards openness. So let me do one thing. Let me just take a step back and just give you a very, very brief overview of ZZY and what we have open sourced there. So for those who have not heard about ZZY or ZZY, ZZY is an optimized and mature post-stack seismic data format with a successful track record of 20 plus years to say. It is supporting efficiently workflows when it comes to seismic interpretation for grid tomography, structural stratigraphic interpretation, and quantitative interpretation, to just name a few. And obviously, we have a huge worldwide representation of this format as such. So if you can see on the slide, we have 40K Petrel users who have been using this format. And we have hexabytes of ZZY files out there. And I would rather like to call it hexabytes of geological insights, because it's not only about seismic amplitude data, which is stored as ZZY, but also a lot of geological insights which you and your customer have created. Example being, it could be edge attributes, it could be quantitative attributes, rock physics properties, and whatnot. And essentially what we have done now is we have open sourced this proprietary ZZY format, and that's what we call OpenZGY. An important point for all of us to take away from this slide is OpenZGY is a rebirth of ZZY in the cloud world, where we have optimized and enabled it for the cloud world, which definitely will bring further benefit to the end user, which Erik will allude to later on this today. Now, one of the key promise which this whole thing brings to our industry is OpenZGY can now be accessed by anyone from any application and platform. That is the most crucial point where I want to give away from this slide. Without the fear of locking into one platform, now an end user can frictionlessly integrate with the OpenZGY to say. Now, there are a lot of benefits with OpenZGY can bring. One of them is and extensible backend storage and compression, which I'll briefly touch on later on. We have also contributed SegY to ZZY binaries for a smooth ingestion workflows for an end user perspective. Next slide, please, Eric. Now, this slide, I'm not going to read through this, but these are the links for the repositories for OpenZGY, seismic data management services, SegY to ZZY converters, which is accessible to all of you, whether you from anywhere in the world to say. And I just want to highlight also the point, the Slack channel you see here is, this is a channel where you can ask directly question to the experts and they will be able to help you on the detailed question you have on any of the components which I'm showing you right now. Next slide, please, Eric. Now, this slide gives us a gist of some key benefits which OpenZGY bring to all of us. So let me start with writing. With the extensibility of OpenZGY, we have now enabled a new wavelet-based compression to ZZY. That's called ZFP compression for ZZY. Now, many of you are probably aware, ZFP is an open source compression from Lawrence Livermore National Lab, and it is being designed for multi-dimensional scientific data. So very well suited for seismic data, optimized for speed. And through our rigorous testing and what we have observed, it is the compression is quite, the noise especially is quite predictable and flat noise spectrum when it comes to ZFP. And with a signal to noise of -60 dB, what we have observed, ZFP can save you more than 70% of disk space. And most critical point here to notice is that with no compromise on the quality of the data. So with this compression, you can actually run detailed quantitative interpretation workflows. When it comes to storage, very lightly again, OpenZGY supports both file-based and object-based storage on-premise and cloud world respectively. So it is catering for both the users which are on the cloud world, but also on the users which are on-premise. Now, when it comes to reading, which is more crucial for us as a geoscientist, you get a direct data streaming. You need not to copy the data locally when it comes to cloud world. Being the nature of ZZY as such, you get random access to the data set. You don't need to really load the full data set in order to access an inline, cross-line, time slice, or a random line to say. And last point here is very quickly on compute. With obviously we have C++ APIs, but Python APIs for OpenZGY definitely open up the world for the data scientists, where they can use these APIs directly for hooking into their data science pipeline, to say this. Next slide, please, Eric. Yeah, so this brings me to the essence of the part I wanted to discuss here. With OpenZGY and seismic data management services being open source to OSDU, it guarantees an optimized seismic data access to a geoscientist for his or her day-to-day seismic interpretation workflow in Petrel or in Delphi. User can leverage on automation through machine learning and obviously deep domain science, which we have built together for years. But the most important point for me here to highlight is that now being open source, you can use it in your application for innovation and creativity without any friction. No import, export, no duplication is required. And I think this is the right place where I will hand over to Eric to demonstrate this key aspect of openness through OpenZGY. Over to you, Eric, please.
Yeah, thanks a lot, Surander, for that introduction, and also for the help from you and your team in Schlumberger to us in Earth Science Analytics in implementing the OpenZGY format in our cloud-native application. So I'd just like to introduce our platform, the EarthNET Platform. This is a cloud-native geodata science platform. It is built with multiple modules. So at the core, there is a data platform that we call the Earth Bank. This is where we can store and retrieve our data and also do all the data cleaning that is needed to have optimal performance in the machine learning workflows. We have a set of data visualization tools in EarthView And all the machine learning workflows and tool sets we package under the Earth AI umbrella. So we have tools there for analyzing well data, for structural seismic interpretation, for quantitative seismic interpretation, 3D property prediction. And on top, we have a module we call the Earth Insight, which is where we compile everything and use all this data-driven insights to support the decisions one makes on top of petroleum geoscience data. So we have prepared a little demo video. We'll show you the message in the video is basically putting the OpenZGY in focus. So getting a seismic data set that was stored in Petrel in the ZGY format, accessing this through the cloud-native EarthNET platform, executing an AI-assisted seismic interpretation workflow, and then accessing the results back in Petrel after the workflow. I'll just try to start that little video here and talk you through it. So point number one is to register the ZGY volume in EarthNet. So make sure we have it in the right place, in the right coordinates. So we access it, in this case, from a cloud repository that we use internally in our company. We give the volume a name so we can retrieve it easily. And the data set that we're using in this video is the Canning data set, courtesy of Geoscience Australia. Very nice and very popular open data set, frequently used in demos. So then we got the coordinates right, moving to Australia, register the survey. So now we're ready to do a little AI-assisted seismic interpretation workflow. We have here loaded a machine learning model that is trained to interpret faults. And this model is predicting, based on the seismic, the yellow lines. And there is another functionality in EarthNet that is extracting the blue fault sticks from the machine learning interpretation. And at step one, the interpretation is pretty good, but not perfect. So we have adopted a little user interaction. So the user can draw the sticks that the machine learning model didn't pick at first attempt. You save these adjustments, and then you retrain the model with a single click like that. As the model is retraining, you can go to another seismic line. The original machine learning model will support you, and you can extract the sticks from that. You do your optimization, insert your own geological knowledge into the process by kind of completing the fault stick interpretation. You do this as many times as you need until your retrained model performs as you want it to do. And eventually then you will save the model and use it to write the output for the entire survey. So there we're going to the save step, just give it a name, the model itself. And then we can go to the models repository. So in EarthNet, all the models we ever make are stored in a repository. So then we get the model, we apply the model. I'm using 4 GPUs here to write it, the output, to make it faster. And I choose to write it in first along the inline direction for the full size of the state set. Apply. And then in the second step, I write it along the crossline direction and apply that. So after these steps, we get 2 output volumes. I'm going to the seismic viewer, opening the dataset like this, and checking the results. So I have here the two volumes, and each of them looks like that. So now I go to a calculator. Well, average the two volumes simply by executing the function a plus b divided by 2, and my a shall be the cross-line volume, and the b the inline volume, or the other way around. Select some color bars to visualize that, and control the limits of the color bar. And now inspect the output in 3D. So it's important that we blend inline and cross-line directions when we're using 2D neural networks, as we're doing in this case, so that we can see faults of all orientations. And then the last step here, actually, in the averaging, I included multiple model outputs as an ensemble workflow to have an even better results. Then we just store that final output as a SGY and open it back in Petrel and co-visualize it together with the original seismic. So this workflow, although we chose seismic fault interpretation as the example, the point is basically that with access to something like OpenZGY, we have a technology that enables really frictionless workflows between the cloud-native EarthNET platform and the standard applications that are mostly used in the industry, like Petrel. So that makes the daily work for the geoscientist much more convenient. So you can move back and forth between Petrel, other standard applications, and the cloud-native ones. So just a few comments on that. So with OpenZGY, we'd certainly like to thank you, Surander, and all of Schlumberger for opening that up. And we see that for a platform like EarthNET, this really helps us leverage. In addition to using the traditional applications like the Petrel, it enables us to leverage the cost efficiency of the cloud-native applications, of accessing the scalable compute resources. As an example, when we used multi-threaded GPUs to write the output here, and GPUs on demand supporting the AI-assisted workflow. The OpenZGY, of course, allows us to capitalize on the abundance of data that exists in the current data repository in the form of ZGY. And it allows us to accelerate domain specific workflows such as fault interpretation, in this case with AI-assisted workflows. So I think this is a really good contribution to support these more frictionless workflows, combining traditional and cloud-native apps. So with that, I'll hand it over to you, Sarah, to lead the Q&A, and thanks everybody for joining the session.